All right, guys, I'm back. And here we go. Keep moving on. So, Stokes' theorem. Stokes' theorem is Green's theorem extended to three dimensions, and circulation is related to a surface integral in three-dimensional space. In there, we need some setup too, again. So we need this, the boundary. And so here, it kind of looks like a chef's hat, but I mean, it is open, so it is inflated in here. Like there is a front and a back to it, and so on and so forth. It is, it's solid. But in this case, you can see the boundary is just a single closed curve. Here we have three boundary curves, and so it's like a pair of pants or something. And here it's a solid sphere, and it's a closed surface, so the boundary is actually 0. So there is no boundary, and that's why we use the empty set for that. Orientation then is going to be the same as before. You always want like an outward pointing normal, or the boundary orientation. When you walk on the boundary, you want to have the surface be on your left-hand side. So this one is boundary oriented, but this one is the wrong way. And again, because if I was here, this is my left hand over here if I'm walking that way, and it would be outside of that surface. So it's the same piece in there. That's what those are meant to tell you. Curl, we went through before, and so I'm going to skip over this, assuming that you watched the previous video, you saw me explain this part of the notes. The curl is it's a cross product, and as such, it should be a vector, and it is a vector when it comes out. And here is that notation for it. All right. Then we had properties of the curl, that it's additive and that it's you can pull out scalars. And then a few of these things about the cross-partial properties that was true for conservative vector fields. It still holds. So if the vector field's conservative, then the curl will be 0 in that case. All right, then Stokes' theorem. So Stokes' theorem says, suppose you got an oriented surface with, and all this is the parameterization. So they usually use g of u and v, or g of theta and phi, or f of x, y, and so it doesn't matter. But that g takes two variables from a domain, and it maps it onto a surface. Okay, and then D is that boundary, and it's a simple closed curve, so it doesn't intersect itself. G is 1-to-1, meaning it's invertible, and it's regular, meaning that the normal vectors and tangent vectors aren't ever 0, except maybe on the boundary. Then what's true is, if you want this circulation, you can trade it for a surface integral over the curl of the field. So somehow the curl contributes to that. Let's see how this works. I'll make a couple comments here. If the surface is closed, then the boundary is empty, and so then the integral on the right would automatically be 0, but that shouldn't be super surprising. Okay, let's look at this. Let's verify Stokes' theorem for this vector field, and we're going to take part of this plane, and it's going to be in the first octant, and we want an upward pointing normal. Okay, so what does that look like? Well, here's the deal. If I let x and y be 0, and I close this off, I can see that x, if I multiply the 2, it covers at 2. If I kill these, z, or the y covers at 3. And if I let x and y be 0, then z hits at 1. And so this is that triangle I see. Even though it is a plane and it goes in all directions, we're just seeing part of it that is in that octant. There is part that flies over here and part that's over, but those are in different octants, and so we don't really care about those. The x, y, and z all positive puts us in this first octant. And upward pointing normal, so I know that the normal has to be pointing up or out. Okay, if we did this the old way, this surface right here it is made up of 3 curves. And so, as such, we need to parameterize the 3 curves. Now, this is way more than you want to deal with or know. But if we took the first curve is down here. That's when z is 0. So if z is 0, then I can figure out what x and y would be in there. And basically you just solve it and you see what you would get as a line in that plane. If x was 0 and we're in that yz plane right here, then we have x is 0, and you can use these values to figure out what that equation of that line actually is. And then if y is 0, we're in the xz plane, and there y is 0, and we can figure out those pieces. All of these use that parameterization of a line, and we're just using points and all of that. So that's 3 curve parameterizations. 1, 2, 3. 3 time values for my my parameter variable, and then I still have to feed these 3 curves into that vector field. So we need that f of c of t, and then we need to dot that with c prime of t. So here's all my f of c of t's. So I have 3 of those. I have an f, so I should have 3 f of c of t's. I have 3 curves, so I have 3 tangent vectors right there. Now I need 3 dot products, so I dot that, I dot that, I dot that, and I see that I get a negative 2t. So then this one is going to be 0, this one is going to be 0, but this one we actually do have some stuff in there, and so I integrate that, and it comes out to be negative 1. Now I know I explained that fast, but you have to remember that you needed to parameterize 3 different line segments. You needed 3 different values for your variable. You had to feed it into the vector field 3 times, find 3 tangent vectors, perform 3 dot products, and still potentially have to do 3 integrals. Granted, by luck alone, 2 of them canceled out and you didn't have to do anything. So, but that's not always the case. And so you could have had 3 integrals to still perform. That's a lot of things. That's 3, 6, 9, 12, 16 steps to do this. And that's just with 3 edges. What if I had like an octagon or something in there? Then now you got 8 of these, and you have to break it down. So that's not always the best way. But Stoke's theorem then said, hey, instead of doing that, just do the curl, figure out the curl, and then use it as your vector field, and then just do the surface integral of that surface with the vector field being the curl instead. So we figure out the curl. It's a cross product, and it's worked out here. You can do it. You know, you pop this, and you get dx dy minus 0, and so all of that comes into play. Then our G map, then I'm just using, and this is still the xy, f of xy parameterization from the surface integral notes. And so I'm just using exactly that piece, and all I did was I solved this for z. So I minus that, and that's why it should be a minus and a minus right there. Now that I have my map, I can figure out my 2 tangent vectors, cross those, and I get my normal vector. Now here's the thing on this. That was kind of a lot of work in all of this, but we knew the normal vector in there because you can see a half is on x, and a third is on y, and a 1 is on z, and a half and a third and a 1 right there. Remember, the coefficients are that normal vector, and so whatever that normal vector is for a plane, and that just worked because this was a plane. So that was a plane, and we know we can just steal, in quotes, the normal vector off of that. So yes, this is good, but in the case of a plane, there was a little bit of material we had earlier in the course that could have obtained that information for us. Then now we have the curl figured out. So now we take the curl and we feed g into it, and g, remember, was x, y, and 1 minus the x over 3 minus y over 2, or whatever it was. Oh, I must have missed them up there. So I feed that in where they all go. Then I need the curl dotted with the normal vector, and so I have the curl dotted with the normal vector. And then I take that domain in the xy plane, and here it is right here. So I look, and on the floor, on the x-axis, it hits at 2, and on the y-axis, it hits at 3. So there's the 3 and the 2. Well, I drop 3 and run 2, so that should be negative 3 halves x, and then I know the y-intercept is 3, and so there I've got the equation of that line. And so then, since that's the case, I'll draw it over here. Since that's the case, this is 2, this is 3, there we have that. This is the line y equals negative 3 halves x plus 3. And that's my patch on the floor. And so if I line this up here with the dy and dx, then y goes from 0 to that line, so 0 to that line, and then x gets to run the whole gamut, and that's 0 to 2. And believe me, guys, when you see that, it is the same, and it is the exact same value that we got before, but there were two different ways of doing it. So we did this problem twice. Once the old way, parametrizing a ton of curves, feeding them to vector fields, finding tangent vectors, dotting that stuff up, and doing all of that. Or we could just figure the curve, the curl, get a normal vector, and do a surface integral using the curl instead of that. All right. Then here I have a note here, so I'm going to jump over for a sec, and I have that note right here. That note is this note at the top. It says, notice that curl f contains the partial derivatives df1 dy and df1 dz, but it doesn't have the partial df1 dx. And so that comes from, where the curl formula is. Right here. In that x slot, there's a df3 dy and a df2 dz, but there is no df1 dx function in there. Similarly, in the middle slot, there's an f1 with z and an f3 with x, but that's in the y slot. It doesn't use the y function, f2, and it doesn't use the y variable at all. And in the third slot here, in the z spot, we're not using f3, which would be the z's corresponding quote-unquote function, and we're not using the z variable either. So what their note is trying, if the function in there, f1, is only a function of x, then those other two derivatives will be 0, and an f1 doesn't give anything to the curl because it would be a 0 in that spot. And the same thing happens like if f1, f2, and f3, if f1 only depends on x, and f2 only depends on y, and f3 only depends on z, then the curl is automatically 0. So the example here is 4. Now if you look, we have this. We have sine x squared right there. Sine x squared, that's only an x function, so it's not going to give anything to the curl. The next one, though, the e to the y squared, that is y stuff, so that will contribute to the curl. But this plus x squared there is not going to give anything. And in the third slot, the z to the fourth will contribute, but that 2x squared, or the z to the fourth won't, but the 2x squared will. And I think I said it backwards over here. The e to the y squared won't, but the x squared will. And so down here, when you see, they say this part, sine x squared, and the e to the y squared and the z to the fourth will all be 0 in there. So you really only have to focus on the curl of the non-variable specific portions of those functions. And so they cut it out to be 0x squared and 2x squared. And that's because in the y slot, the e to the y squared doesn't contribute, but the x squared would. And in the z slot, the z to the fourth doesn't contribute, but the 2x squared would. And in the first slot, that's only an x function, so nothing contributes. And they just kind of factor off or pull out the pieces that aren't going to yield anything, and then it makes computing the curl easier. And so the curl comes out to be 0, negative 4x, and negative 2x. And it says that's by the author's design. We can see that the surface integral is 0 without even computing it, because we see that the normal vector for that plane, they just steal it in this case. But u and the curl are orthogonal, and so notice in a surface integral, we have to dot the vector field, feed it when it was fed the parameterization with the normal vector, and that gives us this little line down here, and it's 0. And so in that case, we have shown that it's 0, and that's what it really said to show. It just said, use Stokes' theorem to show that that thing comes out to be 0. And the Stokes part of it is that instead of parameterizing 3 curves and doing all of that stuff, we just stripped off the part of the curl that wasn't going to contribute, figured out the part of the curl that would, and when we did the dot product, we saw that the scalar that we got was 0, and so then that double integral is just going to be 0, so we don't have to do anything or worry about anything even. All right, so that's that. Down here on the bottom, it says if f is equal to the curl of a, so this is almost like f equaling to the gradient of v. Remember we called v a potential function? So that is, this is the same. So curl is kind of a derivative, and a is a different vector field, and so instead of doing the gradient of a and then a being a potential function for that vector field, if you trade the gradient for the curl, and then if f is equal to the curl of a, and a happens to be a vector field, then a is called that vector potential for f. And it's exactly like a potential function for conservative vector fields. What we mean by that is there is this theorem here that says if f is the curl of a, then the flux of f through a surface S depends only on the orientation of the boundary and not the surface itself. It's kind of like path independence. Remember path, it didn't matter if you walked like this, if you're going P to Q, and it didn't matter if you went straight, and it didn't matter if you took just a half circle, or if you went all the way around the world a bunch of times and wound up there. As long as you started and stopped, the path you took was irrelevant, the value would be the same. If f happens to be the curl of a different vector field, that vector field's the vector potential for that field, and in that case, you get surface independence. And so what you find is that you don't get anything out of it. All right. So then I have here, just to go over example 23. 23 is very quick, and I just want to show it to you because we just talked about something, and so this will kind of shed light to it. So look at problem 23 right here, and it says you know 2 things about a vector field. Part 1, that f has a vector potential a, but you don't get to know a. But you know then that f having a vector potential, then f is the curl of a. So you do know that for sure. And you know that the circulation of A around a unit circle, oriented counterclockwise, is 25. So just around A, if you compute that circulation, it turns out to be 25. And they want you to determine the flux through the surface in this figure 22 with an upward pointing normal. So let me show you what that surface looks like. It's right up here. Kind of looks like a 3-fingered glove. But here's the deal. Since f is the curl of A, it is surface independent. So the value of it only depends on the value of the boundary. And they told us the circulation on the boundary is 25. So the answer to this problem, you guys, is it's 25. It's that easy. Like, there is almost no work to do except to just state that, look, you told me that it's It has a vector potential that you gave me an A, but I don't get to know it, but I know the curl of A is equal to F. Right there, it is surface independent, so I don't care what the surface is, just tell me what the boundary is. Oh, part 2, they said, they gave me what the circulation of the boundary is. Oh, well, then that's the answer for the whole thing. I don't care what the surface looks like. And if it was a 3-fingered glove or a 5-fingered glove or any amount fingered glove, it wouldn't matter. As long as it had the same unit circle boundary, it can be a complete mile-long windsock if you want, and it'll still be 25. So that kind of just shows where it seems like it's out of the ordinary, but or it seems like there's a lot of work to do, but they gave you enough to just reason out that there's not anything that you need to worry about. All right, I'm gonna stop there then for this, and we are going to go into divergence and the divergence theorem in another video. All right, so I'm gonna upload this, I'll post the first one, and we'll get stuff going. All right, take care, guys. Bye-bye.